Lesson 15.2, Graphing Logarithmic Functions. Essential question: how is the graph of g of x equals a times log base b x minus h plus k, where b is greater than 0 and b is not equal to 1, related to the graph of f of x equals log base b x? Well, this is a transformation. This is a transformation of that. And if you remember, what does A do? A is a vertical compression. Couldn't think there for a second. Compression or stretch. It can also reflect over the x-axis. H is a horizontal translation, left or right. And K is a vertical translation, up or down. Okay. And depending on what those values are, depends on what it does. Graphing and analyzing parent logarithmic functions. The graph of the logarithmic function f of x equals log base 2x, which you analyzed in the previous lesson, is shown. In this Explorer, you'll graph and analyze other basic logarithmic functions. So first, let's complete the table for the function f of x equals, and let's do that. So 1.1, you put that in log 0.1, and that gives you -1. Log 1 gives you 0, and log 10 gives you 1. So we got 0.1, -1, that's going to be about right there, probably closer than that. And then 1, 0, and then 10, 1. So it gets real close there, and it curves around. And looks something like that. Complete the table. All right, for this one here. 1 over e equals -1. Natural log 1 is 0. Natural log e is 1. And natural log e squared is 2. So we've got 0, -1, probably about right there. 1, 0, and then e is about 2.72, so that's going to be 1 right there. And e squared is about 7.4. That's going to be about right there. I said 7.4, not 6.4. That's going to be about right there. And get that out of there. And then so we got I kind of missed that one. All right, but you got the idea. Good deal. C, analyze the two graphs from step A and B, and then complete the table. All right. So what do we got? Let's see here. Is that looks to be all on one page right there. Well, anyway. Okay, domain. Well, let's look at the domain of log x. The domain, it starts here. It starts here just to the right of 0 and goes to the right. So that's going to give you x such that x is greater than 0. All right. The range, let's take a look at the range. The range, well, it's got an arrow there and it's got a there. So it's going to get to negative infinity down here and it's going to get to positive infinity up here. So the range will be y such that negative infinity is less than y, which is less than positive infinity. Okay, end behavior. Let's look at the end behavior. So as x increases, f of x increases, and both to positive infinity. And over here, as x approaches 0 from the positive side, f of x approaches negative infinity. Okay, so as x approaches positive infinity, f of x approaches positive infinity. As x approaches 0 from the positive side, f of x approaches negative infinity. Okay, let's take a look at it. Vertical asymptote, what we have one here, and that's at x equals 0, but there's no horizontal. So no horizontal asymptote. There's a vertical one, vertical at x equals 0. And what about the interval? Well, it starts down here, and it increases throughout the interval as x gets larger, f of x gets larger, so it's increasing. So it's increasing throughout the domain. And x-intercepts and y-intercepts, let's see, it crosses the x-axis here at 1, but it does not cross the y-axis. No y-intercept. But and an x-intercept at 1, 0. An interval where positive or negative. Interval where positive or negative. Interval where positive and negative. And if you look, where's it? It's positive when x is greater than 0, and it's negative when when y is greater than 0. So here at x, at 1, it turns positive, and at 1, it turns negative down that way. Okay. So what do we got? Positive on 1 to positive infinity, and negative on 0 to 1. All right, let's take a look at the natural log of x. And let's go back and look. They look real similar, right? Just this one here has a much steeper rate of change than that one there. Okay, so we should be able to answer those questions. This is going to be, the domain is going to be x such that x is greater than 0. And the range, same as before, same as the others, y such that negative infinity is less than y, which is less than positive infinity. In behavior, exact same as before. As x approaches positive infinity, f of x approaches positive infinity. As x approaches 0 from the positive side, f of x approaches negative infinity. Vertical and horizontal asymptote. Vertical asymptote, no horizontal, and there's a vertical asymptote at x equals 0. It too is increasing throughout the domain. It has no y-intercept and has an x-intercept at y equals 0. And it's positive on from 1 to positive infinity, and it's negative from 0 to 1. Okay. So let me jump in here and let's graph these things. Okay, we've got log base 2 x. Okay, and then we have log base 10 x, or yeah, and then we have the natural log of x. So those are the three we graphed. Okay, so we can take a look at it. So they're all very, very similar. And I did that because I wanted to show you here in the book it said, and I think that's a typo. That should be negative infinity as well. Okay? All right. What similarities do you notice about all logarithms of the form f of x equals log base bx, where b is greater than 1? What differences do you notice? Okay. Let's look at the calculator we just drew. What's different? What's the only thing that's different? They all cross through 1, 0. They all get real close to 0 here on the x-axis. They're all increasing. The only difference is the rate that they increase. Okay, so the difference is the rate of change. Okay, they're similar. Well, the domains were similar. The ranges were similar. The end behavior was similar. The vertical asymptote was at x equals 0 on all three. None of them had a horizontal asymptote. They all increased throughout the domain. They all had an x-intercept at 1, 0 and no y-intercepts. And they were positive from 1 to positive infinity and negative from 0 to 1. Let's see. So similar vertical asymptote at x equals 0, x intercept at 1, or x equals 1, all are increasing in the domain. They have the same end behavior. Okay, I believe that ought to about cover it. Graphing combined transformations where f of x log base bx, where b is greater than 1. When graphing transformations of f of x equals log base bx, where b is greater than 1, it helps to consider the effect of the transformation on the following features of the graph of f of x. The vertical asymptote x equals 0 and the two reference points 1, 0 and b1. The table lists these features as well as the corresponding features of the graph of g of x equals a times log base b x minus h plus k. All right, so the asymptote is x equals h. The reference point is 1 plus h, k, and the other reference point is b plus h and then a plus k. Identify the transformations of the graph. Okay, so example 1, A. I'll let you do A on your by yourself, and then when you come back, you can, after you read through it and all, we'll do B together. All right. So here's what we want to do. Given or g of x equals log 2 times log x plus 2 plus 4. So I think first what we need to do is identify the A, the H, and the K. So let's see here. We'll let A equals 2, and that's the A. H equals -2, and there you go right there. And then K equals 4. All right, the transformation of the graph of f of x equals log x that produces the graph of g of x are as follows. A vertical stretch by a factor of 2, a vertical stretch by a factor of 2, and a transformation of 2 units left and 4 units up. All right. So the asymptote is going to be x equals -2. All right. And we're going to have 1, and that's going to make that, and 0, and that's going to make that -1 and 4. And then we're going to have 10 minus 2, and then 2 times 1. So 10 minus 2 is 8, and 2 times 1 is 2, plus 4 is 6. So there's going to be our points. There's going to be our points. And I'm going to have to get to that page. Not a problem. So we had -1. We had, first let's see here. We had a vertical asymptote at x equals -2. I think I used blue for that. So let's do that. All right. And then we had -1, 4 for a point. So -1, 4, that's going to be right there. And then we had 8, 6, that's going to be right there. So this is going to look down like this. And that's going to go up like that. All right. So our domain is going to be x such that x is greater than -2. And we're going to go from -infinity to +infinity on the range. And there we go. That's our first one. Your turn. Identify the transformation of the graph of g of x equals. All right. Read all that. So first off, let's identify A. A equals 1/2. There you go right there. H equals -1. H equals -1. And K equals 2. All right. Now what does that do for us? The transformation So we're going to have a vertical compression by a factor of 1/2. And we're going to have a horizontal translation left 1 unit, and we're going to have a vertical translation, up 2 units. All right. So let's take a look. Okay, we had well, our asymptote, our vertical asymptote, and that's going to be x equals h or x equals -1. So we got one here at -1. And then we had that point 1, 0, 1, 0, and that's going to be 1 minus 1, and that's going to be that's going to be 1/2, and that was supposed to be red. Keep my colors the same. 1/2 times 0, and then plus k, or plus 2. So 1 minus 1 is 0. 1/2 times 0 is 0, plus 2 is 2. So we got 0, 2, and that's going to be right there. And then the next point we had was B1, and let's see, B is right here. It's that 2 right there. Okay, so that's going to be 2, 1, and let's see. So now we're cooking. We got 2 minus 1, and then we have 1/2 times 1, and then plus 2. So that'll give us our other point. 2 minus 1 is 1, and 1/2 times 1 is 1/2, plus 2 is 2.5. So let's find 1, and then 2.5 is going to be right there. So here's our transformation. So let's look at it. See if what we did. I think that looks real good. That looks real good. All right. You can obtain a logarithmic model for real-world data either by performing logarithmic regression on the data or by finding the inverse of an exponential model if one is available. So, since we're going to have to, I'm going to go ahead and put this data in the calculator. Okay, so, and then new document, no, lists and spreadsheets. All right, so first, we're going to go up here and we're going to define it, and we'll call this year, Y-E-A-R, and we'll call this Fox, F-O-X. That's what that biologist is studying. So we got 0, 2, 3, 5, 8, 12, 15, and 18. And so let's go up. And we got 55, 72, 99, 123, 151, 234, 336, and 475. All right. And let's go ahead and graph that. Let's see. On and graph. We'll put year down here, and we'll put Fox up here. What does that look like? That looks like it's exponential, right? So let's see. Menu, 4, 6, and the exponential is 8. And there it is. So this, now you see where the book gets those 62 and whatnot. All right. So go ahead and read through A, and we'll meet back on B, and we'll do B together. Okay. Another way to obtain the model that the biologist wants is to find the inverse of the exponential model. Find the inverse model and compare it with the logarithmic regression model. Okay. In order to compare the inverse of the biologist model, P equals 62 times 1.12. And you can see, if you go back here and look, 62 did a little, what do you call it? Did a little rounding, okay? Did a little rounding. So, in order to compare the inverse of with the model, you must rewrite the biologist's model with base e so that the inverse will involve a natural logarithm. This means that you want to find a constant c such that e to the c equals 1.12. Writing the exponential equation, different color, e to the c power equals 1.12, and logarithmic form gives c equals the natural log of 1.12. So you have e to the c equals 1.12, right? So we're going to multiply both sides by the natural log. So you get the natural log, and then the natural log, multiply both sides. So, and that's e to the c equals 1.12. So c will equal the natural log of 1.12. And if you go to your calculator, and we got the natural log of 1.12, and that gives you 0.113. So, okay. So C equals 0.113, 0.113. That's what we got here, wasn't it? 0.113, okay. Can't put all that to the nearest thousands. Replacing 1.12 with e to the 0.113 in the biologist model gives P equals 62 times e to the 0.113t, or P equals 62 e to the 0.113t. Now, find the inverse of this function. So P equals 62e to the 0.113t, okay, and divide both sides by 62. So you get P over 62 equals e to the 0.113. Write in logarithmic form. So the natural log of P over 62 equals 0.113. And let me see here. You got P equals 62 e to the 0.113t. We divided everything by 62, and we got P over 62. P over 62 equals e to the 0.113t, and then we multiply both sides by the natural log, and that cancels that out. So you have the natural log of P over 62 equals 0.113t. Okay? And then we're going to divide both sides by 0.113. And let's see here. Control divided 0.113. And it gives you 8.849. So we'll say 8.85. So that gives you 8.85 times the natural log of P over 62 equals T. So we divided everything by 0.113. And that gave us 8.85 natural log of P over 62 equals T. So that's how we did that. So the inverse of the exponential function or exponential model is T equals 8.85 natural log P over 62. To compare this model with the logarithmic regression model, use a graphing calculator to graph both y equals 8.85 natural log x over 62 and y equals negative 35.6 plus 8.66 natural log of x. You observe that the graphs are roughly coincide. So the models are basically equivalent. Okay, and let's see. Let's just go back over here, and let's go back. Now, we did all that, so let's see. Doc, I don't know why I did that. Menu, 4, and then hide exponential. So we're going to change this. We're going to go over here, and we're going to make this Fox. And we're going to go over here, and we're going to make this year. Okay, so now we can menu, 4, 6, and then 9, exponential. So it's y equals negative 35.57. Isn't that what it said? 35.57 or 35.6, negative 35.6 times or plus 8.66 natural log x, okay? Natural log of x. So that's where they got that. And then if you go new document, no, and graph, and let's graph those two so that we know what we're talking about. So we got 8.85 times the natural log of, and that would be x over 62, x control divide 62, and can't really see it, can you? Can't really see it. Menu, 4. Oh, there it is. Okay. So there it is. All right. Now let's graph the other one. Okay, let's graph the other one. And so let's press tab here, and then we've got negative 35.6, negative 35.6 plus 8.66 natural log of x and then see they're right on top of each other. They're so close. I mean, you can barely see any white space between them. So they're real close. So doing it by hand, you get real close to what the calculator would give you. All right. Reflect. In a later session, you will learn the quotient property of logarithms, which states that log base b m over n equals log base b m minus log base b n for any positive numbers m and n. Explain how you can use this property to compare the two models in example 3. Well, what that's saying is we had t equals 8.85 natural log, and that was p over 62. And that says that's 8.85, and then natural log of p minus the natural log of 62. Okay? Now, we don't know what p is, but we know what natural log of 62 is. We can put that in our calculator, and that gives us 8.85 times natural log of p minus 36.6. That's not right. What's natural log of 62? Natural log of 62. Natural log of 62 is 4.127. 4.127. Now, so we got 8.85 natural log of p minus, and then 4.127. Okay, so 85 times 4.127. That's 36.5, and we could just say 36.6. And it's no longer equals, it's now an approximation. We did a little rounding. Okay. All right. Your turn. Maria makes a deposit in a bank account and left the money untouched for several years. The table lists her account balance for each year. So let's go in here and let's see here. Let's go ahead and new document. No. And it lists and spreadsheets. So we'll go up here and we'll put year, Y-E-A-R. And we got 0, 1, 2, and 3. 0, 1, 2, 3. And then here we've got balance. And we'll just call it B. B for balance. We'll make it nice and short. And we got $1,000, the first, initial deposit. And then we have 1020. And then we have 1040.4. Then 1061.21. Okay. So we got that. And then let's see here. Let's go to our calculator. We got 1020 divide by 1,000. And that's control. That's 1.02. So now that 1040.4 divide 1020. Control divide 1. Okay, so we're looking at a factor of 1.02, right? 1.02. So 1.02, 1.02, and that one there is 1.02 as well. All right, or approximately. We want to write an exponential model for the account balance as a function of time in years since the deposit was made. So let's just let the calculator do that for us. So we'll go and we'll put year, and we'll put B, menu, 4, 6, and exponential model. So we get 999. Okay. Now, if we were doing it by hand, we would know that A, the initial value was 1,000. And we would know that b is 1.02 because that's what we calculate. So our equation would be f of x equals 1,000 times 1.02 to the t power. Okay, that would be our function. Now we want to find the inverse. We want to find the inverse of the exponential model after rewriting it with the basic base. So we have, let's find out what, we want to use the base e, right? So we got e of c equals 1.02. So let's go in here and e of, I got a little ahead of myself. E of c. So we're going to multiply both sides by the natural log, natural log, natural log, and that gives us c equals the natural log of 1.02. So that's what I meant to do. 1.02. And that gives us 0.0198. So we'll just say 0.02. So c equals 0.02, right? So c equals 0.02. And it's not exact, so it's an approximate. Okay. So now if you have, we'll say b, make this a b, balance. The balance is 1,000, 1.02 t. All right. And now we're going to put the e in there. We're going to put that e to 0.02. So the balance equals 1,000. And then we'll put e 0.02 t, right? Good. Now let's divide both sides by 1,000. So b over 1,000 equals e 0.02 t. And to get rid of that e, we're going to multiply both sides by the natural log. So we have the natural log of b over 1,000 equals 0.02 t. So 1 divide 0.02, that's going to give you 50. So if we divide both sides by 0.02, we get 50 natural log of b over 1,000 equals t. All right, so the inverse, which gives the time it takes for the account balance to reach a certain level, is 50 times the natural log of b over 1,000. Now, okay. Now let's go back. And menu, I meant to hit menu. Menu, cancel. Unsaved documents. There we go. Menu, 4, and then hide exponential. And let's change this. We're going to make this B, and we're going to make that year. Okay, now let's menu 4, 6, and 9 for logarithmic. Okay, it gives us negative 348.82 plus 50.49 natural log of x. Okay, that's what the calculator gives us. All right. So The calculator gives us t equals negative 348.82. So we'll just say negative 349. Negative 349. And then it says plus 50.49. So we'll say 50.5 natural log of x. So this is what we got right here, right? By hand. And this is what the calculator gives us with logarithm regression. And let's do here. On one no graph. So the one we found by hand was 50 times the natural log of, and we got to use x, control, divide 1,000. Okay. And let's press enter. We can't see it. It's probably way down here somewhere. Menu, 4. There it is. So there it is. Now let's press tab and let's put in what the calculator gave us. Negative 349 plus 50 point, what did I have? Negative 50.5 natural log of x. Now it won't be exactly perfect because I did some rounding, but you can see you can't hardly tell the difference, can you? There's a little bit, but that's pretty tight. All right, good. All right, so that was C. Elaborate. Which transformation of f of x equals log base b x change the function's end behavior, both as x increases without bound and as x decreases towards 0 from the right? Which transformations do that? Let's see. Reflections across the x-axis. Reflections across the x-axis. Change the end behavior. And it says, which transformation changed the location of the graph's x-intercept? Vertical and horizontal translations. Horizontal and vertical translations. And that's when h and k not equal to 0. Okay. How are reference points helpful when graphing transformations of f of x equals log base b x? They provide a guide to the general shape of the transformed graph. What are two ways to obtain a logarithmic model for a set of data? Well, you can find the inverse. You can find, find the inverse of the exponential model. And the other one we did is a logarithm. Let's see. Perform a logarithmic regression on the calculator. Or graphing calculator. All right. Describe the transformations you must perform on the graph of f of x equals log base bx to obtain the graph of g of x equals a times log base b x minus h plus k. Well, if a is less than 0, reflect across the x-axis, and also A gives the vertical compression, stretch, whichever, and then translate h units left or right, and k units up or down. Cool. All right, folks, great lesson. Thank you very much. You have a great evening, and we'll see you tomorrow in school.